This is a series of videos showing examples of combined operations for complex matrices. Welcome to Numerical Solutions to C Problems. The problem in this example involves a 3 by 3 matrix containing complex numbers. Before starting the solution, interpret the requirement first. There are 3 operations involved in the notation. The matrix has a bar on top, which means conjugate. There are the subscript I and j with the p bar, and ij means cofactor. After which, there are the moduli, which means determinant. The order of operations then starts with taking the conjugate of matrix P. Next is the cofactor of the conjugate of matrix P. Then, the last operation is taking the determinant of the cofactor of the conjugate of matrix P. The first operation is taking the conjugate. This operation simply flips the imaginary numbers in each individual element. So P bar then is taken as 3 minus 2y for element 1, 1. Going downwards, the elements become 4 plus 3i and negative 5i. From the second column, the first element on top is 2. It doesn't need to change as there isn't any imaginary number. Next is 1 minus 3i, and the last element in the column is 5 minus I. From the third column, there are elements 3 plus I, 4 plus 2i, and 0. This is the first operation. Next is to look for the cofactor of P bar. First is to identify the minor matrices. So by covering the first row and column, the remaining elements are 1 minus 3i and 5 minus I, with 4 plus 2y and 0. When row 1 and column 2 are covered, the minors are 4 plus 3i and negative 5i, with 4 plus 2y and 0. Covering the first row and third column, the remaining elements are 4 plus 3i and negative 5i, with 1 minus 3i and 5 minus I. The minors for element 2, 1 are taken after covering row 2 and column 1. They are 2 and 5 minus I, with 3 plus I and 0. Moving on to element 2, 2, the minors are 3 minus 2y and negative 5i, with 3 plus I and 0. Now with second row and third column covered, the remaining elements for the matrix are 3 minus 2y and negative 5i, with 2 and 5 minus I. To complete the minor matrix, cover the third row and start with the first column. The elements remaining are 2 and 1 minus 3i, with 3 plus I and 4 plus 2y. Element 3, 2 contains 3 minus 2y and 4 plus 3i, with 3 plus I and 4 plus 2y, when row 3 and column 2 are covered. Complete the minor matrix by covering the third row and third column, thus leaving 3 minus 2y and 4 plus 3i with 2 and 1 minus 3i. After taking the minor, create a single element on each minor by taking the determinant. For a 2 by 2 matrix, just take the products of the diagonals and subtract them. For element 1, 1, the determinant is 1 minus 3i times 0 minus the quantity 5 minus I times 4 plus 2y. If done manually, you can employ FOIL method, but you can also use a scientific calculator to come up with negative 22 minus 6i. The determinant of element 1, 2 is computed as 4 plus 3i times 0 minus negative 5i times 4 plus 2y, which is simplified as negative 10 plus 20i. The next element on the same row has a determinant taken as the binomial 4 plus 3i with 5 minus I, minus negative 5i times the quantity of 1 minus 3i, which results to 38 plus 16i. From the second row, the first determinant is taken as 2 times 0 minus 5 minus I multiplied by 3 plus I. This can be computed as negative 16 minus 2i. The second element can be computed as 3 minus 2y times 0 minus negative 5i times 3 plus I. The first term is zeroed out, and through distribution, the determinant is taken as negative 5 plus 15i. The third element contains 3 minus 2i times 5 minus I, less the other quantity of negative 5i times 2. This is simplified as 13 minus 3i. For the third row, the determinant of element 3, 1 is taken as twice of 4 plus 2y minus the quantity 1 minus 3i times 3 plus I. This is simplified as 2 plus 12i. Element 3, 2 has 3 minus 2y times 4 plus 2y minus 4 plus 3i times 3 plus I. Simplify the difference to 7 minus 15i. The last element in the row has a determinant from 3 minus 2y times 1 minus 3i, less the product of 4 plus 3i and 2, which is simplified as negative 11 minus 17i. After simplifying the elements, the last step of taking the cofactor is to take the alternating signs on each element, starting from 1, 1 as positive. Place alternating signs going to the right and downwards. These signs are the scalar of positive and negative 1, multiplied to the determinants, so the cofactor of P bar is created. The third operation in the requirement is to take the determinant of the cofactor of P bar. And since what we have is just a 3 by 3 matrix, we can use Sarri's rule. By this method, we are to start by mirroring the first two columns before multiplying. First, take the positives by computing the products of elements in the diagonals. The first diagonal has the elements negative 22 minus 6i, negative 5 plus 15i, and negative 11 minus 17i. The product is negative 7,300 minus 100i. The second diagonal includes 10 minus 20i, with 13 plus 3i and 8 plus 12i, which result to negative 4,040 plus 1,480i. The last positive diagonal contains the quantities 38 plus 16i, 16 plus 2i, and negative 7 plus 15i. By multiplication, the product comes out as negative 9,012 plus 6,316i. Add the positives and get negative 20,352 plus 7,696i. Next is to take the negatives, which are from the products of elements in anti-diagonals. The first contains the binomials 8 plus 12i, negative 5 plus 15i, and 38 plus 16i. Multiply to negative 9,320 minus 1,240i. The next diagonal has negative 22 minus 6i, negative 7 plus 15i, and negative 13 plus 3i. The product is negative 2,308 plus 4,476i. The last anti-diagonal has 16 plus 2i, 10 minus 20i, and negative 11 minus 17i. Their product is negative 7,300 minus 100i. Just like the positives, add the negatives, which is negative 18,928 plus 3,136i. To take the determinant, subtract the negatives from the positives, and that is negative 1,424 plus 4,560i.